Today we're going to talk about scatterplots and correlation. Today we will move from univariate data to bivariate data. We will graph using a scatterplot. A scatterplot gives a picture of the relationship between two quantitative variables. Here we have some examples of quantitative variables: SAT scores and college GPA, height and weight, the amount of fertilizer and tomato yield, level of education and salary. Be careful. While there may be a relationship or an association between the two variables, there may not be a cause and effect relationship. We'll graph the independent variable, we call this the explanatory variable, on the x-axis, and the dependent variable, we call this the response variable, on the y-axis. Is there an explanatory or response relationship in the examples above? Who is the explanatory and who is the response for each? So from this example here, we have SAT score and college GPA. Our explanatory variable is SAT score. Our response variable is GPA. Height and weight. This could be the explanatory variable, and this the response variable. Amount of fertilizer and tomato yield. The explanatory variable would be the amount of fertilizer. Tomato yield would be response. And level of education and salary. Our explanatory variable would be the level of education. Our response variable would be salary. From your reading, you've seen that a scatterplot gives us a visual impression of how strongly the explanatory and response variables are related. However, since scatterplots are susceptible to scaling, we move beyond pictures and make a quantitative assessment of the strength of the relationship. The correlation coefficient R measures the strength and direction of the linear relationship between two quantitative variables. When we discussed distributions in the first unit, we talked about the center, shape, and spread. In this unit, we will talk about the direction, strength, and form. Direction asks, is the relationship we see positive or negative? Strength asks, is the relationship we see strong, moderate, weak, moderately strong, or moderately weak? Form asks, is form of the relationship we see linear, nonlinear, exponential, curvy? Let's look at some additional pictures to describe the relationships. The first three here all have a positive correlation. However, as we go from left to right, it gets stronger. So here, R is positive and R is increasing. Here, looking at a relationship, it has a negative direction. As we move from left to right again, though, it does get stronger because our R keeps decreasing. In these two pictures, here, it doesn't look like there's any relationship at all. So could R be 0 for this one when there's no correlation? And here, there's no linear correlation or association whatsoever. But maybe this could be quadratic. We don't know. Because it sort of looks like it could be a parabola. When looking at correlation can be positive or negative, and it has some strength. Here in A, our correlation is 0. There's not any linear association between the points. In B, our correlation looks like it could be about 0.25. So I could draw a line and it would look something like that. Here in C, our correlation looks like it could be about 0.5. In D, our correlation looks like it could be 0.75 because the points are getting closer, 0.9 and 0.99. How the correlation coefficient measures the strength of the association, the points get closer and closer to your line that would go through the data. Let's talk more about our correlation properties. The sign of R gives us the direction and association. Correlation is always between -1 and 1. Correlation treats X and Y symmetrically. Correlation has no units. Correlation is not affected by changes in the center or scale of either variable. Correlation measures the strength of the linear association between two quantitative variables. The key word here is linear. Correlation is sensitive to outliers.